Here is a more complex example. Um, and this is where we are finding the definite integral instead of the indefinite integral as we've been doing thus far. Um, and we need to use a substitution x equals 2 sine theta. So, um, as you can see here, what we have, um, and before we actually get into the rest of this question, I'll just explain the thinking behind this example, because I think that's the hardest part of this. Um, the thinking behind this question is that we have this 4 take x squared in a surd, right? So we can't integrate this straight up. We can't integrate it straight up. Your next thought might then be, oh, nonlinear substitution, we have a nonlinear component, we'll just chuck it in. However, nonlinear substitution, if you remember from, a few minutes ago maybe, only works when we have like two functions together, if we have like a product or a quotient or something of that kind. Because then the derivative of our u is going to cancel out, and we're going to be left with no leftover x's. But in this case, we only have one function, so we can't use nonlinear substitution. And I know if this is your first introduction to integration, this kind of might seem like a lot. But if you do want to practice that out and try using nonlinear substitution and write that out, that might also help you understand why we can't use it. Again, it's because we don't have those two separate functions. So the derivative of 4 take x squared isn't going to have anything to like cancel out with. So we're going to be left with this extra x. So following this logic, we know that we can't use nonlinear substitution. But we know we do have to do something to simplify what's under these brackets. And this is an example of when we can use trig identities, not just to simplify a trig function to begin with, but actually to do some substitution. And again, if this substitution does not seem immediately obvious to you, I do not blame you. This is very tricky. I hope, though, that the explanation of why we got to this, or how this is the only option, makes sense. So, the reason that we're choosing to substitute kind of using trig is because we have this surd, and when we're using our trig identities, we often have a lot of trig identities that have a squared trig component and like a constant number. So what we're thinking with this substitution, and we'll get into what actual identity is used in a bit, but what we're actually thinking with the substitution is if we can put this in here, we might be able to find a identity that like leaves this with something like cos theta squared or whatever under the surd. And if we do that, then we can cancel the surd out, which makes our integration a lot easier. So that is where that came from. We're just recognizing that with the trig identities, we have like a lot of, a squared trig function plus a real constant number. And hopefully we can utilize that if we have a squared trig function under here to kind of cancel out the surd, because we don't really have any other option as of yet available to us. Okay. Now that the thinking behind this question is explained, let's get into the actual purpose of this example, past explaining substitution and trig identities and giving a more complex example. And that is to actually explain how we can use substitution with definite integrals as opposed to indefinite integrals, which is what we've been doing so far. So, if we are ever using substitution in a definite integral, we need to change the bounds of the integral And we do this by setting x to be equal to each of the values of the original bounds, then solving for theta. So we'll get into how this is done on the next slide. And just as a quick note as well, there is an easier way of doing this question, which you might have recognized if you've gotten a little bit farther into integration, and particularly all the different functions and trig functions that we can integrate. But we're going to have a go using substitution just because it's a good exercise. Okay, so over here, we have the solution for this question. So we have x equal to 2 sine theta, and then of course we are going to differentiate x with respect to theta to get dx d theta. So this is of course the second step of substitution, where we let our substitution be equal to a particular letter. Then we differentiate that and we isolate the dx. Now, we need to change the bounds. And this is a step that's important when we're getting into definite integrals as opposed to indefinite integrals where we don't have bounds. So as we said in the slide beforehand, we need to let the previous bounds be equal to our substitution. So our substitution was 2 sine theta. Our previous bounds were 2 and 0. So we're going to let 2 sine theta equals 0 and 2 sine theta equal 2. And this gives us that theta is equal to 0 and pi on 2. And this you could get just, of course, by using your table of values or your special triangles. So, again, when we have a definite integral and we're using substitution, we need to change the bounds by letting our substitution equal to the bounds. So, I'm just cracking my back. Excuse me. So, once we've changed the bounds, we now need to apply this to the integral. So, we've put our new bounds into the integral, and then we've subbed in our substitution. So, of course, we have our 2 cos theta d theta, which is our sub-in for dx. So, we have this, and this is coming down here. And now what we did is we let x equal 2 sine theta, and then we substituted this in our surd. So, as you can see in our previous slide over here, we just substituted it in, and then this can simplify to cos squared theta. So, what we did up here is we simply subbed it in and then factorized out the 4. Then from here into our next step, we recognized the Pythagorean identity. So, remember, sine squared theta plus cos squared theta equals 1. So, of course, we just rearranged this to get cos squared theta equals 1. Take sine squared theta, And this is, of course, what we could substitute in here. Moving on from here, we removed this square root, which of course left us with cos theta multiplied then by this section here, which is 2 cos theta d theta, which once again left us with another cos squared theta, which is annoying, but it's better than what we had before. And then, of course, we could take the 4 out the front. So from here, we still don't want the squared in that cos theta. We need to get rid of the squared. And what we can do is use one of our trig identities to get it down to a cos with a power 1 instead of a power 2. So the identity that we used was this one here, which is the cos of 2x is equal to 2 cos squared x, take 1. And of course, then we could rearrange this to isolate cos squared x, which gives us a half cos 2x plus 1. So we substituted this in here. So of course, the half took our 4 down to a 2, divided by 2. But it left us with what we wanted down here, which is 1 plus cos 2 theta. And now we can integrate this easily, just using our regular linear substitution. And we can just apply our definite integral rule. So we're going to keep the 2 out the front. We've obviously integrated, so integral of 1 with respect to theta is theta. The integral of cos 2 theta is going to be sine 2 theta divided by 2. You could use linear substitution here, but of course we just use like the regular rule, which is that if you have, this is what you would have learned in methods as well, is if you have like the cos of ax plus b, then the integral is going to be equal to 1 on a sine ax plus b. And that's what you would have learned in methods. Okay, so we just applied that, and then we applied our regular definite integral rule with our limits. We subbed in our limits, and this gave us an answer of pi. So, as you can see here, the only difference with definite integrals is that we need to sub in our limits and change them a little bit to correlate to the substitution that we are using. But other than that, not much has changed. It's pretty straightforward.